Hey, AP Physics, this is Warner. We're going to look at 2008, number one. We have two cars. A couple students are at an amusement park and they're going to do a little bumper car. This person is riding in the bumper car at 2 meters per second. Their mass and the mass of the car together are 250. This person is sitting still, so their original speed is equal to 0 meters per second. Car A is accelerating to the right. It does it at 1.5 meters per second to a speed of 5 and then continues at a constant velocity. So this car is going to move somewhere to about somewhere there, and we know it's accelerating in that time. And then from here to here, they're going to travel at a constant velocity. So we'll just write constant there. First thing we need to do is let's figure out what the time it takes to go from here to here since it's accelerating. So final velocity is equal to original velocity plus acceleration times the time. Our final velocity is 5. Our original velocity, remember, is 2 for this car, plus the acceleration, which was 1.5 times the time. And we're looking for time, so 5 minus 2 is 3, and that's equal to 1.5 times t. So our t here is really easy. It's just 2 seconds. Let's figure out how far it went. So let's change colors. We're trying to figure out how far it went when it accelerated. So all these things are about the acceleration of that car. For this one, we need to go ahead and figure out how far it went. So let's just say that this x1 distance, x1, is equal to our original speed times time plus 1/2 of the acceleration times time squared. So we really need the distance. We don't have the final speed. We really don't need it in this one. So we're just going to use the equation that we have here. Remember, there were 3 kinematic equations. That's the first one. The second one is here, and then the last one was VF squared is equal to VO squared plus 2AD. So we're going to use 2 of these as a review. So let's find this change that it took. Our original velocity was 2. The time was 2 plus 1/2 of the acceleration, which is 1.5, times the time squared, which is 2 squared. And we find out that it travels a whopping distance of 7 meters. So right here it travels the 7 meters. So we can see from the diagram that the distance it travels for x2, okay, so we're going to say x2 would be equal to the total distance, which is xt, minus x1. And this is the distance it travels at a constant velocity. So we're going to put v constant, just like we did here. Let's go ahead and figure this out. x2 is equal to 15 minus 7. And so we end up with 8 meters is how far it goes when it's traveling at a constant velocity. So let's go ahead and figure out what is what's the time it takes for it to travel this x2 distance. So we can just say that we know velocity is equal to distance x2 over time. So if you rearrange that, the time is just equal to x2 over v. We know that this position change, we said it earlier, was 8 meters. So we're going to put 8 over, and then our constant velocity. Our constant velocity is 5 meters per second. And this 8 divided by 5 is going to give us 1.6 seconds. So we know this is the time it takes to go the second leg. This is the first leg, so this is what we call the first leg and the second leg. And now we want to find the total time, so we're going to say t is equal to t1 plus t2. t1 we said was 2 seconds plus t2, which is 1.6 seconds. So our total time here is 3.6 seconds. That is the first part. That's worth 4 points, so it's kind of obvious where you get your points here. 1, 2. This is actually a point, and then doing all this would be our last point, which is 4 points. For the second part of the problem, they want us to try to figure out after the collision, car B moves to the right with a speed of 4.8 meters per second. They want us to calculate the speed of the car A after the collision. So if we think about it, this collision is a bouncing collision. So we know that it's elastic. So one thing you might want to do is write down that it's elastic. They don't stick together, they just bounce off of each other. And we know that the mass of the first car times the velocity of the first car plus the mass of the second car times the velocity of the second car. But remember, before the collision, this is just 0, is equal to the mass of the first car times the final velocity of the first car plus the mass of the second car times the final velocity of the second car. So now we've got everything we need. We want to find the final velocity of the first car. So we're looking for this guy right here. In order to do that, we need to subtract m2 vf2 from both sides. So we're going to put m1 v1 minus, now we're going to subtract this, m2 vf2, and that's equal to m1 v1f. So to get rid of the m1 from both sides, I just do this. And now my final equation is the mass times velocity, original velocity of the first car, minus the mass of the second car times the final velocity of the second car, divided by the mass of the first car, should give me the final velocity of the first car. Let's go ahead and plug everything in. So this one was 250. We said that our velocity of the first car was 5 during the collision, minus, now we're going to do 200 for the mass of the second car times 4.8, and then we divide all that by 250. Be careful, you can't cross off the 250s here because you have a 200 here. If this was 250, then that'd be more than fine to do. When you're done, you should end up with an answer of 1.2 meters per second. So this is 1 point, just going through and showing this equation that the momentum is conserved, that it's an elastic collision. And then here we just say it's 1.2 meters per second. For the next part of the problem, it says indicate the direction of motion of car A after the collision. So here, remember that we said our final velocity of the first car was equal to positive 1.2 meters per second. And because of that, we know that this car has got to be going to the right. It's got to be going to the right. And you actually get 1 point for just checking that one thing. And then we have one more thing to solve for. It says, is this an elastic collision? And it is not totally elastic. So it's not totally elastic is what we're going to say. So not totally elastic. And the reason it's not totally elastic, and so therefore it's kind of in between an elastic and a oh shoot, what do we call it? An inelastic equation. We're going to say no, and then we're going to justify our answer. And it's because in an elastic equation, in an elastic collision, the final kinetic energy should be equal to the original kinetic energy. And here, the kinetic energy is not conserved, so it cannot be totally elastic. So for this one, we need to prove it. We're going to say that the original kinetic energy is equal to 1/2 of the mass of the first car times the velocity of the first car squared. And the final kinetic energy should be equal to 1/2 of the mass of the first car times the velocity of the first car final squared. And we need to add to that 1/2 of the mass of the second car times the velocity of the second car squared. So let's go ahead and plug our numbers in. For this one, we're going to have 1/2 of 250 kilograms times 5 squared. Remember, this is only for the first car because the second car velocity is 0. If you do all this math, we end up with 3,125 joules. And then here we end up with 1/2 of 250 times 1.2 squared plus 1/2 of 200 times, and then we said the final speed was 4.8 squared. So now when you're done, this should end up being 2,484 joules. Where did some of that energy go? It probably went into sound, and it went into a little bit of heat. Do remember that earlier we did say that this was an elastic collision. There is some bouncing there. But the problem with what we did, it's really not a problem. It is elastic, but it's not totally elastic. So totally elastic would mean that you would conserve all of your kinetic energy. And so we just really, if we want to, we can call this a partially elastic collision. So it's just partially elastic. We do lose a little bit of energy. And that is the end of this question.